So we looked at the energy balance, and we said when we don't consider the convection, there is a jump at the surface between the temperature of the surface and the air just above it, right? We need convection to equilibrate the two at some time scale. But let's get to that in steps. So let's first look at the vertical structure of the atmosphere. So here it is going from the surface to about 110 kilometers, and you can see that there are multiple layers. So troposphere separated with the tropopause from the stratosphere, which is separate from the mesosphere with the stratopause, and the mesosphere is separated from the thermosphere with the mesopause. And at each of these pauses, the temperature gradient changes direction, right? You are probably already exposed a little bit to these structures, at least the troposphere and the stratosphere. The energy balance didn't tell us anything about this structure, but nonetheless you probably heard that all the energy that comes into the surface that we talked about warms the surface, as we saw, and then temperature decreases with height up to a certain elevation above the surface, and then something happens that makes the temperatures begin to warm again. So that's the troposphere, where all the weather happens where we live, and stratosphere is called stratosphere because it's stratified. And we mentioned earlier that basically the sun's electromagnetic spectrum has many bands of UV, very high energy short wavelengths to lower energy longer wavelengths. So the bluish UV gets absorbed by the oxygen molecules to split into oxygen atoms. We'll see the reaction in a little bit. The oxygen atom combines with the oxygen molecule to form ozone. Ozone absorbs some other wavelengths of UV and so on. So these endothermic reactions in the stratosphere warm the stratosphere. Then in the mesosphere and thermosphere, you begin to have very rapidly decreasing density of air. So you have few molecules of oxygen, ozone. We'll see the ozone where it maximizes, but you have ozone all the way into the thermosphere by the same process of UV bombarding oxygen and splitting it and forming ozone. And you have CO2 molecules and so on. Essentially what happens is these molecules are absorbing energy from UV at these various wavelengths, and then there is very little mass to send the energy back into space. So thermosphere can get as warm as 1000 Kelvin. So that's why it's called thermosphere. And then above that, basically the very vacuum, almost like a vacuum, the molecules actually get ionized, and you get ionosphere, which begins to reflect radio waves and so on. So when people talk about space weather, they are talking about these kind of weather which matter for communication, for satellites, and so on. Okay, so most of our attention in this course is in fact going to be in the troposphere, not even into the stratosphere. But stratosphere is obviously an important part of the structure that we worry most about for climate change and so on. And also because of ozone hole, where CFCs damaged the ozone in the stratosphere and allowed more UV to come in. And also remember again that ozone in the troposphere is not a good idea because it's a highly potent greenhouse gas, plus it's very bad for your lungs. It's a pollutant. Okay? So that's the structure in brief, and the simple calculations we will do here shows that there is a mass-weighted mean temperature of the atmosphere, which is 255 Kelvin, which we derived with our simple greenhouse balance without the atmosphere. Top of the atmosphere balance can be done very simply by taking the short wave coming in and the long wave that has to go out with the Stefan Boltzmann law, sigma TE to the fourth, where TE is the emission temperature, the effective emission temperature. Okay, we saw the complications with that and so on. The other thing to remember is that anytime you look in the atmosphere, this average profile of the atmosphere, of course it changes with latitude and so on, but this profile is almost always there, which means whatever is happening with all the hurricanes, the thunderstorms and the subsidence and the so on, rising over the mountains, there are processes that seem to bring the profile back to this average lapse rate, or the decrease in temperature per kilometer. So what are those processes that do this? That's what we need to learn. So here is the profile of oxygen. As you see, it maximizes around 20 to 25 kilometers, and temperature again going from the this is showing in terms of ozone partial pressure, not temperature. So the scale, you have to be careful. So temperature in the troposphere drops off to the tropopause and then increases into the stratosphere, and then you have the mesosphere and the thermosphere. This is for a particular day, 2nd January 1997, which was just before the big El Nino of 97 and 98 hit. The concept of local thermodynamic equilibrium that we had used to define temperature, where we said the turbulence is isotropic and molecules have an equal chance probability of hitting another molecule in every direction, isn't so valid when you go into a region where the density is very low. So temperatures are often not measurable directly in that sense. Okay. The other thing we'll come back to is our favorite Clausius-Clapeyron, the exponential temperature dependence of water vapor. Right. So looking here at the height in the atmosphere in terms of pressure. So it's not just the temperature that drops off with height in the troposphere. The pressure also drops off, and you can see that it is not linear. So there is a drop. We will see what is the height of E-folding. You haven't heard it before, don't worry, we will define it. And we look at water vapor pressure in grams per kilogram. What do we see? Basically, we expect that near the surface temperatures are warmer because tropospheric temperature gradient is drops off as we go. Gradient doesn't drop off, the temperature drops off as we go above the surface. So warmer air, more moisture. So we have higher moisture near the surface, and moisture drops off as you go in the upper atmosphere and reaches basically zero. It's the same obviously as we go towards the poles, because even at the surface the temperatures get colder, which means humidity drops off as you go from the tropics to higher latitudes. So let's come back to the other properties in the next podcast. But when we look at the vertical structure of the atmosphere, we are slowly moving towards the dynamics, starting with something very cute called hydrostatic balance. Where did hydrodynamic come from? Hydrostatic balance. I think you already kind of put together the words and imagine what it is. Hydrostatic. It's important in the atmosphere, as we will see.